Hi, AP Chemistry. You just left me. There's the sign on the whiteboard about the yearbook pictures today for juniors. So I am actually doing this. You just finished up lab number 4, the alum lab. You were working on stoichiometry, so I am going to give this one a go. This is chapter 4 still, but it's the second half of chapter 4. These are redox reactions. And we are going to do assigning oxidation states first, then we'll go into balancing. Again, chapter 4 is very big on the AP exam. So let's jump right in, shall we? Oxidation reduction reactions are referred to as redox for short. We love our shortened names. We're a very lazy society, so we call them redox. Very important to remember that the driving force of a redox reaction is electrons being transferred. Remember the driving forces. The driving forces of a metathesis is the removal of 2 ions from solution. The driving force of a redox is the transfer of electrons. So a completely different driving force from metathesis. When we assign oxidation states, the actual charges when you do ions is the number and then the sign. Oxidation states are not actually charges, but sometimes they are similar to the charges, is going to be the sign and then the number. So oxidation states are merely bookkeeping. A lot of times they're very similar to what the charge of an ion is, and a lot of times they are not. It is just bookkeeping of the transfer of electrons. Alright, take a look at these 3 examples, and what I want to know is which one, or 2, or all, is a redox reaction. Notice that for my first example, I have a compound and a compound, so this guy is a metathesis or double replacement reaction. Notice for this one, it is not a double replacement because I don't have 2 compounds in the reactant side. I have an element and water. So this guy, if you recall from your first year chemistry, is actually a single replacement. And I'm going to assign oxidation states, but I'm going to give you the rules in just a moment. Element +1, -1, -1 +1, and 0. Notice that the sodium went from a oxidation state of 0 to +1, and the hydrogen went from +1 to 0. So they have a change in oxidation state. So this guy is a redox reaction. Take a look at example number 3. This is not a metathesis. This is actually a halide replacement, a single replacement that comes under the category of halides. And I am going to check my work again, and again I will give you the rules in a moment. 0 for an oxidation state, +1, -1, +1, -1, and 0. Notice that the chlorine went from a 0 oxidation state to a -1, and the bromine went from a -1 to a 0. So again, there was a transfer of electrons. So example number 2 and 3 are redox reactions. So a couple of things to remember from your first year chemistry is recognizing reactions. This is a single replacement. So redox reactions will include but are not limited to single replacements, combustion, decomposition, and synthesis. In first year chemistry, all you had to do was recognize them based on how they were written. Now you're finding out that these are actually redox reactions and a transfer of electrons occurs in them. Alright, oxidation states. This is bookkeeping, just pure and simple bookkeeping. Yes, some of them will be very similar to the charges, but it is really just keeping track of the number of electrons being transferred. Oxidation states are numbers assigned to atoms to keep track of electrons in redox reactions. Electronegativity plays a very important role. Oxidation states only represent the actual charge in the case of ions. So they're similar sometimes to the charge of an ion. Other than that, your oxidation states are purely bookkeeping numbers. You're keeping track of the number of electrons that gets transferred. So we're going to go into the rules. The net charge on all neutral compounds must sum up to be 0. An atom in its elemental form, and that includes the diatomics, has an oxidation number of 0. Group 1A's oxidation state is exactly like the charge. Group 2A is the same, exactly like the charge. And aluminum in group 3A has a +3 charge. So those three are very similar to the ion charge. Similar to charge of ion. Notice again that the oxidation states are the sign and then the number, and of course you should already know that the charge is the number and the sign. Okay, so just a little variance there, not a big thing. Okay, so going on beyond that, hydrogen, when bonded to a nonmetal, will have an oxidation number of +1 and a -1 when bonded to a metal. So what the heck does that mean? And we will do examples. What that means is that in a situation, and I just showed you an example, let's see, oxidation when it's a nonmetal. Here's your nonmetal. It's actually the positive end, and when it's attached to a metal, it's actually going to be the negative end. So sodium, which is rule number 3, and hydrogen, and that's what that means. So hydrogen will have a different oxidation state depending on what it's attached to. Fluorine. Fluorine is the most electronegative element on the periodic table. It will always be the negative end. Nothing supplants it. The other halogens are usually, note the emphasis on usually a -1, but that will depend on what they are bonded to. The more electronegative halogen will be the -1. Oxygen is going to be a -2 unless it's a peroxide or bonded to fluorine. Then it's going to be a positive. And with regards to peroxides, peroxides are traditionally group 1A and 2A, never transition metals. Oh, I shouldn't say never. That's such a harsh word. Usually not transition metals. So if you see CrO2, that's not a peroxide. And then finally, the polyatomics, the oxidation state of each substance in a polyatomic must sum up to the charge of the polyatomic. Okay, so we're going to do a little practice of assigning oxidation numbers. First one on the list is carbon dioxide. According to the rules, oxygen is a -2 unless it's attached to fluorine or one of the other halides, which it's not, or it's a peroxide, which it's not. So my oxygen is going to be a -2. I assign the oxidation states on top of the formula, and I put the math on the bottom. Each oxygen's a -2, and there are 2 of them, so that's a grand total of -4. This is a compound, so my oxidation states must be equal to 0. So I have to have an oxidation state of carbon that, when added to the oxidation state of the oxygens, must be equal to 0. My carbon must be a +4. There are my oxidation states on top, and I do the little math work on the bottom. Sodium, the ion sodium, will have an oxidation state of +1. All group 1A will be equivalent to its charge, so the oxidation state of this ion is +1. Magnesium sulfate, I am going to actually separate this. I'm going to put it over here. Magnesium, there's the ion that makes up the compound. Here's the polyatomic that makes up the compound. Group 2A ions have the charge, so my oxidation state for the magnesium is a +2. I'm actually going to work on this guy now. Oxygen is a -2 unless it's a peroxide or attached to fluorine, which it's neither of those, so it's going to be a -2. There are 4 of them. This is a polyatomic. The sum of the oxidation states must add up to being a -2. If I do this work, then X comes out to be the sulfur in the sulfate polyatomic has an oxidation state of +6. This one's nice and simple. This is a diatomic. That is its elemental form. Its oxidation state is 0. Here's a situation where you have 2 halogens bonded together. Fluorine will always be the negative end, so fluorine is going to be the -1 end. It is a compound, so the oxidation states must add up to be 0, so chlorine is a +1. Here's a polyatomic, so I'm going to tackle that one over here. This is the nitrate polyatomic. I have to assign oxidation states to the nitrogen and the oxygen so that when they add up, they will be -1. Oxygen is a -2 unless it's a peroxide or attached to fluorine, which it is not, so -2. There are 3 of them, so my nitrogen has to have an oxidation state that, when added to -6, will be equal to -1. That means my nitrogen has to have an oxidation state of a +5. And again, just bookkeeping. It's not its charge. That just is related to the number of electrons it might lose. All right. This is hydrogen, which is attached to a nonmetal. So the hydrogen is actually the positive end. And there are 4 of them. That means my carbon has to be the negative end. And carbon the electronegativity of carbon is greater than the electronegativity of hydrogen, therefore carbon, and it's the little three lines, carbon is the negative end. So if you're trying to decide, electronegativity will rule. Ooh, here's an unusual one. So what I'm going to do is basically figure this out using the rules. Sodium is in group 1A. It's always going to be a positive 1. Of the chloride and the oxygen is more electronegative than the chloride, and it is not a peroxide, so it's going to be a -2. Oxygens are -2 unless it's a peroxide. That leaves chlorine to be a +1, and if I add up all the oxidation states, I get a 0, which I should because it's a compound. Elemental oxygen, nice and simple, 0. Now this one's a little odd. Can you come across fractions for oxidation states? Yes. If you do this one and assign the oxidation state for hydrogen, again, it's the least electronegative of the two. Carbon has the higher electronegative, so carbon will be the negative end. Hydrogen is a +1. So here's my math. I have to have some number, an oxidation state of carbon multiplied by 3 added to the 8 hydrogens being equal to 0. If you do the algebra, you get a -8/3 for the oxidation state of the carbon. And yes, that's very odd. Are you going to come across a lot of those? No. Do you have to know they exist? Absolutely. So it's very important to know that that is totally possible.